Good morning, physics class. It's problem set 35, day number 3. Let's begin. Okay, first thing we want to talk about is speed of sound in iron versus speed of sound in air. So let's pretend that we have a set of train tracks, and on this train tracks, way down the line, we have at 5.6 kilometers away, we have this train. I hope you love my train drawings. They're classic. And here's the train. It's got the little steam engine at the top. Doot, doot. And this reckless observer, Daredevil, puts his ear to the ground and says, can I hear the train whistle in the rail first, or can I hear it in the air first? So let's do this. There's a couple things we need to know. We need to know the speed of sound in the air is 350 meters per second. That's given to us. And we also need to know the speed of sound in iron. I gave you a little table that has that on it. You can also find that in the previous video. But we know that it's 5,120 meters per second. Now this week, I've got it all in iron. And please be careful, because maybe next week in the problem set 36, I might change that so that it's in copper or gold. I know they don't make railroad tracks out of gold, but let's just pretend, okay? So we'll start with 5.6 kilometers. You notice that both of these formula units are in meters per second, so we need an equivalent unit. So we're going to say 1 kilometer is equivalent to 1,000 meters. And then kilometers are gone, and we want seconds. So we're going to use the reciprocal of my formula unit. And we'll start by calculating the time in air. So it's going to take 350, every 1 second, it's going to travel 350 meters. So we use our little bit of unit analysis, 5.6 times 1,000 times 350. We get a grand total of, 5.6 times 1,000. And I said times 350. I meant divided by 350 equals the time is going to be 16 seconds. Now let's do the same process. So this is for air. Let's do the same process this time for iron. So we'll get 5.6 kilometers. And again, we're going to multiply by the 1,000 meters that it takes. Then we're going to do 5,120 meters per second. We're going to use the reciprocal just like we did before to get the time it takes in iron. 5.6 times 1,000 divided by 5,120 gives me 1.1 seconds in the iron. So iron wins. So iron is faster, and I have the times of both that the sound will travel through both mediums. All right, now this next question. We got something called the combined gas law. PV over T equals PV over T. And in this particular question, it says right here, pressure is constant. Pressure is constant. So we could go and we could take pressure right out of the equation. We get V over T equals V over T. Last week, I had a combined gas law, and it had a little GIF of the gas laws kind of floating around. And I explained that sometimes a gas law will be a direct variation. As one goes up, the other goes up also. Sometimes the relationship in a combined gas law will be an inverse variation. So I got two multiple choice questions I'd like to see if you could answer before I complete this video. Is the question we are working here, is this working on Charles' law, Boyle's law, or Gay-Lussac's law? Okay, and is this a direct variation or an inverse variation? I like on LMS they give you an option to have quizzes that can be automatically graded. I'm thinking about having problem set 36 be a multiple choice one where I ask you. I've been threatening all year that I was going to do a concept thing where I'm going to ask major concepts. I'm thinking about it. I'll let you know a little bit more next week. Okay, but first let's convert our temperature. So we got 24 plus 273.15 and 72.5 plus 273.15. We have to convert these to kelvins because in order for these gas laws to work, they have to be in absolute temperatures. So we're going to say 24 plus 273.15 is 297.15, and 72.5 plus 273.15 is 345.65. So now we'll apply it without taking in pressure to account. So our initial volume is 1.864. Our initial temperature is 297.15. Our final volume is what we're looking for, and our final temperature was 345.65. All right, we'll cross multiply 345 plus 0.65 times 1.864 to get 644.2916 over 297.15 equals the final volume. So we'll divide by 297.2916 to get the final volume of 2.167. We had four significant digits in the question, so we'll have 4 in our answer. So there we go. We also have T1 as equaling 297.2 K and T2 equaling 345.7 K. So those are my answers. The critical thinking question, in the end, you would say that this is Charles' law. That should be gained from what we learned last chapter. And this is a direct variation because we see the temperature goes up and the volume goes up. So as one increases, the other will also. Another critical thinking question, which one would be the one where you had an inverse variation? Next question is going to take us a little bit. Actually, I was just working on this video a minute ago, and I started all over again because I made a critical error. I left out a 5 out of my whole question. So I started my video over after like 19 minutes in the first time. So 275 meters high, and we have this bullet fired, and the bullet's initial velocity is 250 meters per second. The angle of ascent is 65 degrees. Now there are some questions that were asked is how far did the bullet go? So it lands over here at the final horizontal position. It says what was the maximum height. So if I kind of was doing my free body diagram and I wanted to connect the two, the final height, we'll call that Y max. And we need to find the final speed. So we're going to say the vertical velocity final. The velocity vertical final. That's going to save us a ton of time. And maybe next week I'm thinking about adding in the concept of that the final velocity has both a vertical component and a horizontal component. And that ends up being a rectangular value. Remember the difference between rectangular and polar form? So if we want to finish this velocity part right here, at right now, all I want to know is the velocity the vertical velocity right before it hits the ground. When we get a little further, I'm going to say there's also a horizontal component, and we want to combine the two using polar, but that takes a lot more work, and I'm going to need to dedicate a slide just to that concept in order to get that. But this will begin to introduce us to the concept. And we also wanted to find out how long it takes for the bullet to hit the ground. All right? So let's start with the distance equation. The distance equation is going to say, I'm going to use y final because I want to work on vertical. That's the only reason I chose that. It equals acceleration times time squared over 2 plus velocity initial in the y direction times the time equals the original position in the vertical direction. That's why I'm using y. It's very different when you work on the vertical versus the horizontal. The final vertical position, which I'll show you what I'm talking about, that occurs right here when it hits the ground. That value is 0. Conversely, the other value where it leaves the ground, the vertical position, is positive 275. We've gotten to the point this year where we know that acceleration divided by 2 is negative 4.905. That should be something that's just in your brain because it's gravity, negative 9.81 divided by 2. We've done that so much this year that you should understand the concept by now. All right? And then the velocity initial in the y direction is found by 250 times the sine of 65, and that's t. All right? So this was the 5 that I left out. I got way far along the problem, and I realized I left that out, and I got frustrated and just deleted the video. So anyways, 250 sine 65